Okay, so what is the number of parameters of O3? So before I talk about this, can someone guess what would be the number of parameters? I mean, I've already told you, but well, can you give me a rationale, the physical or geometric rationale about what would be the number of parameters of O3 of a matrix?
You would have an angle of rotation about the z, x, and y axis, so that's why you would have 3.
Yeah, and what about the discrete transformations?
The determinant condition basically imposes a condition, and that reduces one parameter.
Okay, yeah.
And similarly, we can
Similarly, we can
also consider the relation of the transverse to the inverse, and that also reduces down the number of independent parameters we can have.
Exactly. Okay, so coming back to Saif's way of thinking, which is because we have 3 rotations, there should be 3 parameters for O3. But what about the discrete transformations?
Oh, I hadn't thought about those. Yeah, I was just thinking about the rotations.
No, it's good. Well, if you think about the discrete transformations, there are no continuous parameters there. Okay. Those are discrete transformations. There is no continuous parameter. So adding those discrete transformations doesn't really change the parameters, the continuous parameter space. Okay. Okay. So let's look at O transpose O, this condition. So if I write it now in matrix notation, then it's O transpose Ij, O of Jk is equal to delta of Ik. And there's a sum over J. J goes from 1 to 3. Now, in general, we will use the Einstein summation convention. And the Einstein summation convention is that if there's an index that is repeated, then the sum over the range of that index is implied, unless explicitly stated otherwise. So this equation can be written as O transpose Ij O Jk is equal to delta Ik. Okay, so the sum over J is implied because it's repeated. So O transpose Ij is OJI, right? That is the definition of transposition. So we get how many equations are here, independent equations are here. Noting that this is symmetric in I and K. Okay, how many independent equations are there here? Can you guys think about it and let me know?
3.
Can you explain?
So we'll first have like 3 equations because like we're multiplying 3 by 3 matrices. So you'll equate. Oh, okay. So it'll be 9.
It'll be 9, but it's symmetric in I and K.
Oh, okay. So that will like make all the equations similar, like which the off diagonal things, like the diagonal elements that are diagonally opposite to each other, 1 equations each.
So like 1,
reduce-
3 and 3, 1 are the same.
So that's like 3 plus 3 and 6 reduces down to 6 independent equations.
Right, so there are 6 equations here. So there are 6 conditions on 9 real parameters, right? Real continuous parameters. So that means that the parameter, the independent parameter space is 3-dimensional. Okay, and this is called the dimension of the group. So the dimension of a continuous group is the number of real parameters, number of real independent. Okay, so we can say that dimension of O3 is 3, right? Which is 9 minus 6. Okay, so that's the dimension of, so that was, I think, comment number 2, or maybe 3. And that should have been, yeah, comment number 3, should. And then number 4 is that O3 has an infinite, uncountably infinite number of elements, right? This is not a finite group. So that means that the order of the group doesn't make sense anymore. So yeah, we don't have any Lagrange's theorem or anything like that for continuous groups. But a lot of the construction, like the coset construction, those things go. Okay, I think this is a good place to stop. I just wanted to give you a flavor of what these continuous groups are. Are there any questions?
I have a question. So could you explain what exactly is a parameter space? Because I think you started using it, but I'm not sure if you explained it.
Yeah, that's good. I kind of explained it when we were talking about GLNR, but yeah, I should have explained it again. So, O is a 3x3 matrix, which has some symmetry properties, right? So that means it has, it's a 3x3 matrix, so it has O11, O12, O13, then O21, O23. Okay, so all these OIJs are real entries. So in principle, for a random, for an arbitrary 3x3 real matrix, an arbitrary 3x3 real matrix, would depend on 9 real parameters, right? Right? But because of the conditions on O, because of O transpose O, equals to 1, but because of O transpose O equals to 1, only 3 of these 9 parameters are independent. Okay. So these are the sort of the parameters, the parameter space. Okay. In fact, the manifold that these numbers correspond. So these numbers are coordinates on some manifold, and that manifold is actually with a canonical metric can be identified with a group. But that's that's more of a formal property. But at least does this answer your question, Sai? What I meant by parameters?
So the parameter space would be R3. Is that right?
Locally, it should be R3, but not globally. Yeah.
Okay.
Globally, it's actually a lot more interesting. Globally, we're going to see it's going to be a 3-sphere, which is of course locally R3, right? With the opposite points identified. And it's to get to this conclusion, we will use the fact that, okay, this is going to, that we will use the isomorphism, the first isomorphism theorem.
So what does the S3 refer to? Is it like the SU2?
No, yeah, it's SU2, yeah. So it's the parameter space for S3, SO3, we will see at some point in the future, and this is going to, this is something I want you to understand eventually, and sorry, my sphere is not working out today. That it's going to be a 3-dimensional sphere where all the opposite points, the antipodal points, have been identified. So locally, of course, that is still a manifold and looks like it looks, well, it is a manifold, not locally, also globally, but it's locally it looks like R3, but globally it's not R3. Okay, so that's something we'll see, Saif. So, but all you need to know now is that its dimension is 3. At least that should be clear.
I had another question, like, so the introduction of the concept of the dimension in the case of groups felt a little, not so concrete to me. Like how do you actually think of the dimensions? Like, for example, if it was the vector space case, then we do have a idea of what dimension is, but like, what about the dimensions of discrete groups? Or
well, the idea of a dimension in a discrete group doesn't exist, but in a continuous group, what happens is that we will see that the continuous group, another name for them is Lie groups. And one way of defining a Lie group is that a Lie group is a group which is also a manifold. And a manifold has a dimension.
oh, yeah,
and that dimension, that dimension is going to be the group, the dimension of the group. Okay. Locally, it'll be whatever number of independent parameters you have.
So you mean this formulation in terms of number of parameters is kind of a reduced version of what we get by working with manifolds?
Yeah, you're just counting here. You're just counting the number of. You're not saying we are not figuring out yet what the range of these parameters are, or what sort of topology they have, or what kind of geometry you can put on them, right? Those are much more. This is a crude sort of argument about what is the dimension of the space.
Okay.